The Pi instrumentation framework also adds a bit of overhead. So the real executions times would be more like 20 seconds down what says here. So for PDC about 40 seconds to analyze the sample, and for R2 it would be it was 77 seconds, so about 50 something seconds. Okay, and then further optimizations, because those previous times were already acceptable for us. Of course, the IDA version runs faster in, like I said, 15 seconds for that particular sample, and further optimizations can be made to so the real execution times would be more but like I also 20 seconds I decided to stop there optimizing and continue in a near future. So for and on the meanwhile I did some other things that can also help to reduce the time, which was to add FLIR signatures to 77 seconds to detect library functions and skip them, because usually you don't want to and then further optimizations because those analyze times and find matches across these statically compared already library functions for us. Of course, so how it works is you can put any number of .sig files on this directory here, and they will all be used to scan the binary at the startup. So the real executions and any function that matches those signatures. Meanwhile, these signatures that you can find here, they are signatures for the UCBC function, the library functions, and I bundle those because for my use case, as I was analyzing IoT malware, UCLibC is a common with the implementation found in malware. Already so yeah, but you can feel free. So how it works is you can put any number. This is an optional feature by the files, and can be also turned off, and they will all be used to scan the binary at the startup. So how do you use it? Any function that matches those signals. As this fork of the code that you can find here uses MySQL and Radar, you need those installed on your machine. Well, Radar and I bundle locally, and then the MySQL server can be remote or local. Once you have the setup done, you can go to this file db.json and then fill in there the credentials for your MySQL server, and then the only thing left would be to install the requirements for the script itself. Once you have all that, you can run the script. It's pretty straightforward. The only thing you need to do is to, if you pass it a single file, it will analyze that file, generate the diaphora database for that file, and exit. The database name will be the SHA-256 of the sample to avoid collisions in names. And if you send two files to the script, it will analyze both of them and generate both databases, and then compare the databases using the diaphora algorithms. Then some options: if the default behavior, if the database already exists, is to skip the analysis because it's already done. But if you, for whatever reason, want to force to generate the database again from scratch with the -f command line option, you can do it. Then if you provide two files and the comparison is performed, the default option will be the default output will be an HTML file. The original diaphora, what it does is that it shows you the results in IDA directly in a window. Of course, we don't have that here, so this is what I did to visualize the results. And the default name for this file will be the first 10 characters or the first file's hash underscore vs underscore, and then the first 10 characters of the second file hash. .html for of course. And with -a you can disable the skipping of the library functions. So by default it is being done. With -a everything gets analyzed. And now I had prepared some demos. The first demo uses a Sakura sample set. Sakura is a GraphQL variant. It's not particularly special or interesting or anything. It's just yet another GraphQL variant. I chose it because it had one debugging symbols, and also it was one of the first variants that I came across while I was developing this project. So this is my sample set. If in case you want to reproduce the results or try at home or whatever, they are, as you can see, they are all ELF files, and there's a bunch of different architectures in which this bot is distributed. And this is the easiest comparison. It's I did it as a basic test to check that everything was working correctly. And for example, in this by the way is the generated HTML file. And this you can see here that we are comparing this Sakura sample, which is an ARM sample, to this other Sakura sample that it's also an ARM sample. And you can see some stuff. That first of all, these functions here, it says that it matched them 100% of the code in them, and it's because the matching description said that they have the same clean pseudocode. But it's also, they are also very small functions, which just one basic block each, and probably they are also small in size. So maybe these functions are wrapper functions or just a jump or something similar, and it's being matched because they are very small. One thing you can do to fix this, in case they are not real matches or that you don't want to match these kind of functions, is to only analyze as the same as being done with Flirt. You can also add a condition for a minimum number of basic blocks, for example. That's still not being done in the code, but it's very easy to do, and I'll probably get to it in the coming days. But for the rest, you can see that they are very nice matches. The ratios are very high, and you can check they are true matches because, as I said, both samples have debug information, so you can see the function names, and you can see how the matches both have same names and the same amount of basic blocks. So yeah, you can check easily that those are true positives. Moving on, then a bit of a harder test. This time we are still comparing within the Sakura sample set, but now we are comparing two different architectures. Here we are comparing an Intel x86 sample with an ARM sample, and now you can see this in the results, that first of all the number of matches that previously was 40 has decreased to 18. Of course, across architectures it's harder to match functions, and also that the ratios have gone down, but this is to be expected because now that the functions are different architectures, they are gonna be more different. But still, you can see that the results are very nice. Again, the names are the same and the basic blocks are the same, so we can easily assume that they are actual matches. And lastly, this would be a Sakura sample in 64 compared against Yakuza which is another GAFKit variant sample, ARM also, so cross architecture and cross variants. And still the number of matches, of course, continues to go down as it is expected. The ratios kind of maintain themselves in about 0.75. And again, the matches, you can check that the names are the same, basic block are the same, so we can conclude that it's able to produce good matches across variants and across different architectures. So that's it for the first demo. And now a second demo. I thought, when I was writing this project, I came across this blog post from Maptics, and there you have the link if you want to read it for yourself. Also, by the way, this demo is done with the bigger project I was talking about previously, not with the R2 diaphora, although the bigger project is mostly a layer on top of it to ease the process that I was describing previously. So yeah, as I was saying, the blog from Aptics, they claim that they have found Mirai code from the Mirai source code leak in some GAFKit samples, and they showcase this hash, this sample that's also extracted from the blog as a showcase that their findings. So now here we have some screenshots also extracted from the blog for their claims. They say this is the Mirai source code or part of the Mirai source code leak, and these windows that have GAFKit on them are the sample that I was referring to in the previous slide, this one, that if you recognize the window, it's the hex phrase, the compiler. And yeah, they say this the source code highlighted in yellow has been found in GAFKit samples here and here. Oops. Okay, so I thought it would be fun to test these claims with my own project to see if I could also see these findings on the sample. So what I did was I downloaded and compiled the Mirai and GAFKit source codes, the leaks, and in every architecture they are usually distributed. And then I added the most prominent functions to the indicator database. And by most prominent functions, I just mean do not add like we saw previously a wrapper function or a library function, something identifiable enough that can generate meaningful matches. And then I ran the r2 diaphora script comparing the database generated for the blog sample to my indicator database, and the result was this. I got 9 matches for GAFKit, which I have excluded most of them because they were not meaningful for this presentation, and 1 match for Mirai. And if you remember from the screenshot, these functions and TLS and holes and std that match GAFKit are the ones here that they say Aptic says it's Mirai. So I was getting this function match, but not to the supposed family that they should match, and I was getting a Mirai match, but another function. And if you have seen, if you are familiar with GAFKit and Mirai source codes, you may remember that GAFKit is the naming convention on the function is usually camel case, and the naming convention for the Mirai source code is usually a snake case. So it makes sense that these functions are actually GAFGit, and this function is actually Mirai. Actually, also, if you because among the first screenshots, there's a Saint HTTP function in the aptX blog screenshot. If you look for that function on the original GAFGit source code leak, it's not there. But if you search this prototype from the just write it manually from the screenshot and search it on Google, you will end up in this link, which is among the first results. And if you visit the link, it says original Qbot, which is another name for GAFGit, modified by XFIFA version 4. So it's indeed GAFGit, those functions that they were previously claiming. But yeah, although it is true, however, that there was some Mirai code in the sample, just not the functions that they were claiming they were. Yeah, that will be all for the second demo. As for future plans, because the work on this project is far from over, on the near future I plan to keep optimizing the performance. I would like to match the performance of the IDA version. There's also a missing feature. The IDA version of the script obtains about 42 or 43 indicators for each function, and there's one missing in the current Radare version, which is the pseudocode primes hash, and this is because the pseudocode primes hash uses the abstract syntax tree of the decompiler. And for Radare, for the compilers I'm using, Ghidra and PDC, they do not offer an AST, or at least they do not offer access to the AST. So for this to work, you will need to generate an AST from the pseudocode obtained with whatever the compiler you are using, which is doable, but a bit more work. And also, in general, the IDA version currently is generating more matches than my version. So yeah, I also plan to work on improving the quality and number of matches, and make sure it's they are all the matches that you can generate from the binaries. And yeah, also some random more usability features, like creating a pip package for easier usage and all that. If you are interested in the code, the link is there. Of course, it's public. If you want to contribute as well, drop me a line, write to me in Twitter, for example. And yeah, if also if you were interested in this presentation and thought it was a cool project or liked it, we are currently hiring in my team. Positions are not very yet official, so if you want to join or are interested or want to see what's there, by the time being, send me a Twitter DM, for example, and I'll move it. Yeah. Now, if you have questions or there are questions, I'll check the YouTube chat as well. Let me, because the previous, there's on Google Slides one question. Maybe you said, but I lost for the string crash. Is this open source and published somewhere? R2 Diaphora is open source, yes. The code is here. You will have the slides available as well, I think. But it's just my name, R2 Diaphora. And the bigger project, it's unclear yet if it will be open source or not. I will try to make it the open source, but since it's a company project, I would need to ask for permission to open source it. And yeah. Let me check if there are more questions in the stream. No, it looks like there aren't any. So yeah, I'll wait a few minutes, and if there are not any questions, that will be all.
Thanks, Fernando. It was a great presentation. I'm very sorry for the connectivity issues that we had, but the original video was being streamed in a different link. So I have the full backup of the video, and all the presentations will be uploaded later. So thanks for watching. Now we are going into the waiting scene again, and then we'll start the next presentation, which is the one about r2con. Hey, welcome back. We are sorry for the waiting. We know that we are a bit late on the schedule, but we'll tap soon. We're going to start the presentation of r2con. So yeah, let's begin. Murphy, it's your time.
Thank you, Pancake. Well, welcome r2con. This is a talk related to r2n. It's a new tool, a new feature that we are working on in their tool. And the idea is just to have an environment to install multiple radars into your computer, and as well to easily install it. So who we are, my name is Alex, as known as Murphy. I'm a security researcher and an r2free trainer and fanboy as well. And well, we have as well Sergi or Pancake, that all of us we already know who is it. So just
we can skip the slide.
Yeah. Okay, so the problem is that you know that sometimes you're ready for a specific version. However, you need to download all the source code, maybe to install different tools in your computer, or to link to different libraries, and maybe you can have some issues with that, and it just complicates the whole process to, for example, have different versions of a specific binary. That this can be useful for different use cases that I'm going to talk just right now. So the idea is just to solve that problem with r2n. That just it's the idea of the solution is just to have like a tool to centralize installations of radar and all of its plugins, including all the different versions, all the different packages, and install it in a specific way to easily install it in your computer and move it or switch into different versions to avoid to depend on different tools to compile the software, or just to easy the whole process to have it. So next slide. So the idea of r2m, or just in what it's based on, it's just to have like a package manager for different radars in your computer. It's just the same idea that we have in different languages like Node with MVM, or Ruby with RVM with Ruby, or Rust app in Rust, or PyEnv in Python. So the idea is just to have like a package manager to install different radar versions in your computer easily, without depending in a tool chain for compile the whole source, and just working only with packages. Just download the package and install it in your computer. So that's the idea. So we are reinventing the wheel. So maybe yes, but the idea is just to simplify the whole process to install radar in your computer and in different platforms. As for example, Frida does, because it's quite easy to install Frida in different environments, just using pip install. So the idea is quite the same. So next. So the idea is just to, first of all, it's just install r2f, that it's based on Python, and it's uploaded in PyPy. So the idea is just to install r2m using pip install r2m, and to use it, it's just putting a new command in your system to manage all your radar installations in your computer. So next. The first thing is just why Python. We are all the time blaming for languages, and especially Pancake. It's the main hater. However, the main win using Python is that it's working for almost all the platforms, and it's quite easily installed. Maybe sometimes it's even installed by default. So it's good to use it for these kinds of situations where what we want is just simplify the whole process of the installation process, and different use cases. So if we are, for example, developing a new feature, maybe what we want is just have a stable radar in our local system, just to test that everything is work as expected, and then we want to have like a developed version as well in our system, just where we are developing the new feature, and what we want is just testing, just do some regression testings to verify that anything it's broken, and just to check that everything is working as expected. So with r2m, the idea is just to have, we will be able to have different radars installed in our system and easily change to one or another depending on our needs in that case. And the most important thing is just we are going to avoid to pollute the system or to installing things in system paths. So the idea is just to install all the things in your home library to easily install it and easily as well remove it. So that's the main idea. Next.
Okay, so let's speak about the backends. So yeah, when you use r2m, you basically have different ways for installing r2. So usually people will pick the code from Git, and they will download the code and just build a thing from it. The thing is that you can also build that from, you do a new release, or you basically provide a tag. GitHub provides a link to get the target list for that specific version. This is also supported. There is also ways for getting the release binaries. So if you want to install R2 from one, we're talking about Windows, for example. You want to install one specific version of R2 for Windows. It will basically download the builds from GitHub directly. So the thing is that when you're building from source, there are different ways for doing that. I mean, we all know that you can build R2 from using Mason. We can also build that with ACR. It's also possible to get that in zip or tarbles. You can also get like the pre-configured dependencies at compile time, or you want to be maybe to catch them. So there are like different options, and we will try to. I mean, right now it's working with the simplest and more straightforward method. But the idea is that there will be options for picking all the different ways for building R2. Also, additionally, as long as many distros are also packaging R2 and also distributing it, r2m is also able to handle apt, brew, package util, and choco for downloading and installing the version of R2 that fits in your system by just picking the package from the distro. Okay, so, but the thing is that we are not stopping here. It's fine to install R2, but usually when you're using R2, you want to have some plugins, like maybe R2 Deck or R2 Frida. And the thing is that when you are switching between different versions of R2, if you have the plugin installed in your home, the plugin won't be loaded. What it will be happening is that it will be taking the binary and not load the plugin. But if you use R2amp, you can have the same plugin installed for every single version of your installation of R2. So you can have, because as long as everything in r2m have a different path, it will be using a different home for loading the plugins. So you can easily switch between version of R2 without messing with problems with plugins or keeping the same plugins that you had working for one specific version. This is great if you are testing R2 or you are using it in a serious way, like you want to have like a stable version and you don't want to be changing things or experimenting. And you know that you will have like a self-contained working environment that it will work for you. So we are also packaging some plugins. The idea is that eventually we'll be able to package and distribute different, almost all the plugins that we have in R2PM right now. But for now, I'm just focusing on supporting R2 Frida, R2 Ghidra, and R2 Deck, which are probably the main packages. And obviously, or eventually, we'll add Yaito and maybe R2 app or other user interfaces for web UI also packaged in here. Right now, it's working on Linux. I'm testing this from Ubuntu 18 and above. It's also working on macOS. For these platforms, I mean that you can get binary packages for this, not building. Because building R2, it works actually in all the systems. You can use R2amp in Haiku, you can use it in Serenity OS, in any operating system that basically you can have Python and configure Make or Mason. R2amp is smart enough to determine if it's needed to use Mason or ACR, depending on the system or depending on the software that you have installed. I will pick the best option. And for Windows, for example, we'll be taking the zips from the release page. So you can have like stable builds of R2 that are compiled in the CI. And that's it. In the near future, we'll be also adding support for CD and Android, so iOS, Android for adding binary packages over ignoring the Cydia packages, or also supporting the packages in Cydia, and also for Termux. The problem in Termux is that they are only storing the last package. So if you have like one old version of R2 that was working for you and you upgrade, there is no way to go back. The reason for that is because there is some infrastructure issues. Termux is kind of like a huge project and it's managing so many software, and as long as it's not like it's maintained by the community, so there is like a lot of people using that, so it gets saturated frequently. So I will say that we'll be picking the Termux packages out of the release page of R2. And all this process is done in the CI, so we'll be improving the CI eventually for supporting more targets. And if you're interested in new operating systems, just you can make a pull request or you can open an issue and we will have a look. So yeah, we're looking for contributors. This is a call for everyone that is using R2 and wants to have this feature, which is having self-contained R2 installations and being able to switch between them easily. We are open for contributions. We will update the configuration files after every release. Actually, r2m helped us to identify some issues in the build and installation process of R2, and r2m is also tested in the CI, so yeah, that will be improving over time. We want to add more plugins, we want to add some documentation, we also want to have some checksums to verify that the stuff that we are downloading is the one that is we were expecting. And it will be also awesome if we can integrate r2m in a benchmark test suite. This means that the CI is not a good environment for testing performance, because you don't have full control of the system, and it's virtualized and it's shared between many zillions of users. So at the end, the benchmarks that you run there, it can be changing over time. So it's not really something you can trust. But we can have like a setup with a local machine only dedicated to run this thing, and using r2m to switch between different versions and running a test suite for checking the time that takes for running some specific test. It will be great, because this way we can identify some performance regressions and other issues, or also get some numbers if we want to know how much better is the next version of R2. Okay, so the stuff that you can see in the right side of the screen is basically the help message that you get out of running r2m. I will say that it's pretty straightforward and easy, but I guess that it's better to explain that. So you have like the flags for checking the help version and so on, but probably the most interesting ones are the -m for picking if you want to build the package using Mason instead of ACR. So by default it will be using ACR. But if you want to get the binary package, you will have to use the -p flag. -p will tell the backend to download the binary packages from GitHub or the distro, depending on the target system. In the actions, first of all, you will need to call r2m init. That will be creating the r2m directory. This is required because by default, it will be creating the directory in your home. But you can specify this environment variable, the r2m path, which by default is empty, but empty means your home. So you can change that path and you can have like a different r2m in different directories. We can get some configuration options, display them. It's basically a JSON file. We can add new package. Add means downloading, building, and installing. Then we can use, because it's using stow. I mean, I don't know if you have already played with the GNU package system, but yeah, it's basically a package system that's close to Nix, but in a completely different way. But it's based on GNU make, and you build a thing and you install stuff in one specific path. But in order to get that software ready in your path, your system path, you need to stow that binary or all the files that are in the home of this application into the system directories. So r2m is using also stow for that. So you have basically one directory for each build of R2, and then with stow you use one specific version. So you switch between versions by changing the stow of the files. There is also a shell, so if you run r2m shell, you will get a shell into the environment. You can list all the packages and you can get the path that is being used right now. And if you are tired of this, you can just purge the whole thing, and it will be removing all the installations and freeing the disk space that you have been using. So it's demo time. I will go for showing the source code first. So this is the home directory. I didn't set the slides, but you can find the source code of this in this GitHub URL. In there you will and you can just type make. I will be building the thing and installing it. So in path, we can use -l or list for listing all the viable package and all the installed packages. Right now, this is kind of work in progress, so we are actually, I mean, the whole thing is working. It's not a non-working project, but some command line flags and options may change over time. So this is the reason why we're looking for contributors right now, basically for testing and verifying different versions of the package and so on. So right now, in this case, I have r2frida 540 and 542 installed. And I'm using this one. So if I use r2m use r2 5.4.2 and we list them again, we'll see that we are not picking this installation. There is like different packages there. I will say that you can install r2frida, r2deck, r2ghidra, and also r0. And there are these versions. We can go back in time and create more packages for previous versions, but it's probably not really something we are. Let's have a look at how the program works. So internally, if you go into the r2m directory, you will find the source code in Python, but there is also some folders. There is a config folder that contains the configuration file, but there is also the profiles. Let's go into the profiles. And this is the JSON that describes all the database of packages that you can download. So basically all the packages, descriptions, and availability for the binary pack web. It's not something external, so if you upgrade r2m, you basically get updates for all the r2 packages. So you will basically just need to run pip install -u r2m to get new builds for r2 if you want to update them. Okay, let's go into the shell, and if you check into the path, we'll see that there is now a new path created there. So let's change there and we'll see what's going on. Here we have all the binaries, and we have, I mean, we've seen that the bins are basically executable, so we are not symlinking that, but we are symlinking the actual bin directory, which is pointing to the version one. You see that there is like a folder containing all the versions that we have compiled in there, and there is the current version installed and the source folder. Into the source folder, we have the source for each of the programs that we have installed. And this is the path that r2m is using for building. So yeah, apart from that, I will say that you can just use r2m. I mean, right now we use r2. We are using the installation from the package, so we can use that. And if I quit the shell, I will use the one from my system. And yeah, that's it. I think that there is not much more to show in here. Hopefully everything was clear. But if you have any question, now it's your time. Otherwise, we'll go into the waiting scene and you can open issues into the repo or ping us in Telegram, Discord, whatever. Thanks. Tap on the schedule time. So now we have the presentation from Abdel Hotit, and he will be speaking about the integration of Swift for supporting Swift in Frida and R2Frida.
Hello everyone, my name is Abdurrahman. I'm a security research engineer at NowSecure, and today we're going to talk about the Swift bridge in Frida. So our roadmap for today will begin with some words of wisdom, then we'll go through a background that's required to understand some parts of the bridge. Then we'll go through the metadata that is included in Swift binary and how we can leverage that to build the bridge. Then we'll go through the Swift calling convention and our implementation of it as well. And then we'll go through how we can leverage both the metadata and the calling convention implementations to implement an instrumentation primitive in the bridge. Then finally, we'll go through the future of this bridge. So I like this quote from the Pragmatic Programmer book. The gist of it is that the software is more like gardening and less like engineering, because there's this sense of constant growing of the garden and improvement to its overall health. And this might seem obvious, but the reason I'm bringing this up is that while I would love to show some impressive demos, but the Swift bridge is still not at production capacity. So the aim of this talk is to show how we implemented the bridge, what's required to understand how to contribute to it and how to actually contribute to it. So first, for a background, there is this distinction between static and dynamic dispatch, and dispatch is basically how methods are called or how our method calls are emitted by the compiler during the compilation process. So for the static approach, the compiler knows the address of the function and it emits just the static address during the compilation process. Whereas this is what Swift uses, by the way, and whereas the dynamic approach is that the calling of the function to a runtime system. So instead of like hard coding the address of the function, it tells the runtime system, or it emits a call to the runtime system, and the runtime system is what actually calls the method at runtime. So for example, here we have on the left the disassembly for a Swift function call. The other on the right being an Objective-C function call. As you see, the Objective-C, you have to give it a selector. Selector is basically the method name, and then a self pointer to the class or the instance of the type the type in question, and then the runtime handles the actual calling of this method. The Objective-C message send is one of many different C APIs that are exposed by the Objective-C runtime. To allow some very nice primitives that allows to get class list, look up class by name, copy the protocol list, even add some methods to the classes at runtime, and like get the number of arguments, even getting like offsets for instance variables. And it's a very dynamic runtime system. Now, the Swift does have a runtime system as well, but it's not as dynamic as the Objective-C one. So you have some primitives for like casting objects and getting their type and checking if they conform to protocol, but there is no any primitive whatsoever that is reflection in the sense that the Objective-C runtime is. So we're not able to like enumerate types, classes, structs, nothing of that sort. And actually going back to this slide, this API is what the whole Frida Objective-C bridge is built on. This is what allows us to essentially be able to call Objective-C code from JavaScript, because we rely on this runtime API to be able to interact with objects, send them messages, and do all kinds of useful stuff. So does this mean that we can't have those kinds of primitives in Swift binaries? It turns out that we can for a large degree, because Swift binaries retain a good amount of metadata in the hard coded in the binary. So for Mach-O binaries, you have the text segment, which includes a few sections that are related to Swift. One is the Swift 5 types, and this is, of course, all this talk will be talking about Swift 5, which is API stable. So this section is an array of relative pointers. Each pointer points to, and we'll see what a relative data structure is. Basically, a data structure containing a lot of metadata about a certain type, like its name, its fields, its methods, if it's a class, and so on and so forth. Then the Swift 5 protos section includes an array of relative pointers as well. Each one points to a protocol descriptor, and it's just what it sounds like whenever you define or declare a protocol, includes its name, number of requirements, and so on. And we have as well the Swift 5 proto section. This section includes an array of relative pointers. Each pointer points to a protocol conformance descriptor. This data structure is emitted whenever you have a type conforming to a protocol. So if you look at it, you have the protocol type reference, which is the type that conforms to this protocol, the witness table pattern, which we'll get to later. The flags tell you some optional stuff about the protocol conformance, whether it's, for example, it's class only, and all kinds of useful stuff. And we have as well the field MD section. This section is an array of field descriptor. Each field descriptor contains a type name, a field record size, and other metadata such as whether it's constant or a variable. And this data structure is emitted by the compiler whenever you have a field in a struct or a class. So so this is the kind of metadata that exists in Swift binary and even more. So the context descriptor that we saw on this slide, this is in compiler lingo, it's called nominal descriptor. And this is the C++ code in the Swift compiler that emits or parses this binary data structure that we saw here. And this is very useful because we're able we'd be able to reverse engineer basically the binary representation of this data structure by corresponding it with this C++ data structure. And what the bridge does is basically parses this same binary metadata, but instead of having it as C++ code, it's TypeScript, which is the language that the bridge is written in. So for example, if I know that target relative pointer occupies 4 bytes, I know that the access function pointer, the one next to it, will be at a 4 bytes offset, and the one next to it would be at an 8 bytes offset, and so on. And we'll see in practice what this exactly look like, this reverse engineering process. And another example of metadata or nominal descriptors is the target enum descriptor, which include enum cases. This is just to give you an example of what kind of metadata exists in the Swift binary. A lot of useful stuff. Another data structure that's very useful is the type layout, and this will come in when we implement the calling convention, which is very important, that this type layout data structure, as we will see later. But to give you an idea about it, the size versus stride distinction, stride is basically the size, but it's rounded up to a certain alignment, the alignment of the type itself. Another concept is this concept of value witness table, and value witness is like a mathematical concept. This table is a list of gadget methods used by the compiler to perform operations like copy, assign, destroy about certain types that it doesn't know anything about them. By anything, I mean its memory layout or ownership semantics. Ownership semantics is basically who retains the type, who releases the object, who releases the object, whether it's the caller or the callee, and so on and so forth. And the memory layout is if it's a struct, is it indirect, is it inline? Inline means does it have to be passed directly in register, or do you have to pass it by reference? And the reason this value witness table exists is that when you think about it, for functions that have arguments that have protocol types, we know that this type or this argument conforms to this type, but we have no idea at runtime what the ownership semantics or what its memory layout looks like. How do we assign it to some other variable? How do we destroy it? How all those kinds of operations. So basically the value witness table acts as a generic proxy for those operations. And as examples, there is the initialized buffer with copy of buffer value witness, which is just what it sounds like. It initializes a buffer with a copy of another buffer for a certain value. The get enum tag single payload. This one is if you have an enum whose single payload, it has like a case with a payload, and this case is of the type in question that has this value witness table, then this function allows you to get the tag of the enum. And the tag is basically the case index from 0 to however many. And there's some reason why you have to do that as opposed to like parsing it directly. But what it comes down to is that you have to have a proxy method. You have to have a generic proxy that allows you to do those kinds of operations because they differ from each type. And at compile time, we have no idea about those kinds of info. So this is what the value witness table is for. Another thing is that it tells you whether it's inline, and this will also come in very handy for the calling convention, as we'll see later. So the APIs that we built around all of this is the Swift.module, Swift.classes, structs, enums, protocols, and even the types that belong to certain modules. And I want to make a note about the distinction for modules here, Swift modules. So they don't necessarily correspond to, there is not necessarily a one-to-one correspondence between Swift modules and binaries or dilibs. And the reason for that is that some Apple internal libraries have types that belong to different logical Swift modules. So this is why this API exists. So let's see a demo of the metadata, how to actually parse the metadata manually, and the APIs that we have for in the bridge and R2 Frida support, which was implemented by Pancake. So for to see what the metadata looks like in practice, or like the binary representation of it, we have this dummy.swift file, which is like the file on top of which the whole test suite for the bridge runs. So you have empty class, simple class, loadable struct. Yeah, so in theory, as we said, each one of those types should have a record in the Swift 5 type section. So if we were to open up this dummy binary in LLDB, and we look at the Swift 5 types section, and we dump, for example, 10 decimal words, you have these numbers. These numbers are all relative pointers, and it's relative because to actually resolve this pointer, what you need to do is to add this offset to this pointer, and this is probably for storage or memory usage optimization, or maybe there are other reasons that I don't know of. But anyway, to resolve this pointer, what we'll do is to look up the symbol that exists there. So you do this, then you add the offset, and as we saw, there is the nominal type descriptor for simple class. This is a debug symbol. This symbol wouldn't normally exist in production binaries, but the metadata still exists. So if I were to strip this binary, this data would still exist, but this debug symbol right here would not exist. But of course, it's helpful. And looking at the code, looking at the metadata code, we have the type context descriptor. So I know this is a class, so this is a type context descriptor. And I know that the name exists at an offset of 8, and it is a relative pointer. So if I were to first, let's dump a few relative pointers. Give me 10. Yeah. So 8 from here is this offset, is this pointer right here, and it's also a relative pointer. So if I were to resolve it, excuse me, simple class, which is the string that represents the name of the class. So this process that I showed right here is basically the essence of everything that is related to metadata when it comes to the bridge. You just read C++ code and you correspond it with the binary representation, then you build code in whatever language of your preference that parses this code. And of course, in this case, the language is TypeScript. So this is how to parse metadata manually. And of course, there are all kinds of other data that you can feel free to explore on your own. So another thing that we wanted to show is the API. And for example, let's bring up the Twitter app. Free.Twitter. And the reason I said this is not yet production ready is that if the Swift.modules API takes a few seconds to load, and this is because we load all metadata at once, and which is not a very wise decision, but it's very easy to optimize and improve. So we have, these are all the modules that are implemented in the Twitter app. So if I'm interested in one of them, so let's say for example swift.modules.twitter, I don't know, URT, for example, it has 20 classes, 6 enums, 6 protocols, and 6 structs. So looking at the classes, I have some class called URT timeline, vertical grid, and so on. I have an init method, I have some fields as well, and I have the conformances, what protocols does this class conform to. Basically, this allows you to write a very, very nice class dump tool on top of this. And even optional ones, yeah. And if we look at the protocols we have, let's for example look at this one. You have is class only true, so this is a class only protocol and number of requirements. And we have as well, let's see, enums. We have title style, normal, social proof. I wonder what that is. And the conformances, yeah, so all kinds of metadata that is available in the Swift binary would be able to parse by this API. And recently, very recently, Pancake added this nice r2con2021 support for it. So this is the demo effect, taking a bit of time to load. Alright, looks like it's going to time out, so let's kill it and relaunch. Yeah, so it's this command, t, which dumps the types. It will first of all dump the modules. So if I were interested in this Twitter commerce module, it gives me the protocols in a nice pseudo Swift syntax. You have the enum class and so on, and even method addresses, which is very nice to have. So yeah, this is the metadata part. Now, with regards to the calling convention is two-partite. The first part is the physical lowering, which is implemented by the, first of all, the calling convention is called Swift call. It's implemented by the backend, which is LLVM. It's usable by these Clang attributes, and it passes and returns structs of size less than 4 registers directly in registers, so as to be efficient. And on ARM64, X20 is used for the self pointer, as we saw earlier, and X21 is used for the error return pointer. So if a function throws an error, this is the pointer where the error will get stored. And we'll see in practice what this looks like in the demo. So how do we implement this? So to implement this, this was inspired by a previous Frida Swift bridge that was in r2con, I think 2018. So this approach is basically that we just in time compile some adapters to handle the translation from system V to Swift call. And this is very simple actually. If you try to call a Swift function, it will, if you pass it a context, it will load this context into the x20 register. And if a value gets returned directly in registers, keep in mind that we can't clobber x1, x0, x1, x2, x3. So what we do instead is that we store this value in a side buffer, which is the return buffer right here, and then we return them by other means. But the point is that we don't clobber the registers. So it's this store register offset API, the writer API in Frida. And we'll see later what this actually looks like in practice. This like prologue that stores the x0 or like the directly returned values in the side buffer. So semantic lowering is done by the compiler's front end, and it means figuring out whether a value is passed indirectly and its ownership semantics. And its ownership semantics mean basically who retains it, who releases it, the caller or the callee, and it's out of scope for our use case, but what we are really concerned with is whether it's passed indirectly. And some types have to be address only, even if they are less than, if there are structs that are less than 4 registers, because their type layout is not known at compile time. So generics and protocol parameters, for example, we don't know their exact type at layout, so they have to be passed by address. And some types need to be registered with a runtime at all times for memory management purposes, such as structs that have weak references. And the value witness table comes in play here because it includes the indirectness, whether the value is indirect, and we have as well the type layout, which we parsed in the metadata, which is very useful because if we were to parse arguments or we were to call arguments, we have to know how many registers it occupies, right? So this kind of info is available in the value witness table and the metadata as well. So the APIs that we have for the calling convention is the Swift.native function. You pass it the address, the return type, archetypes, context, and error. Return type could be a Frida native function compatible type, or could be a type that's retrieved via the metadata APIs that we've shown earlier. And another API is the protocol composition, which basically emulates the ampersand syntax to like make a protocol composition out of multiple protocols. So let's see what the calling convention looks like in practice and the APIs that we have for it. So I have this file called convention.c. This is a C program that is very simple, just has one struct that is big, that is larger than 4 registers, and the other is normal, which is 4 or less than. And we populate them with some values, and we define the function with the Swift call attribute. Both of those functions, the test big and test normal. And in theory, when we pass the big, it should be passed as a pointer, not directly in registers, because it's more than 4 registers. Whereas the test normal, this one should be passed directly in registers. So if we were to look at the disassembly of this, you have the main test normal, as we've seen, is passed from x0 to x3, whereas test big, you just have the x0. And even if you want to see this at runtime, we can launch this and set a breakpoint at test big and test normal, and then launch. So remember that test big should have the struct passed as a pointer, and it is, and it's a stack pointer. And here we see the values that we populated from AA to EE. Now, if we were to go to test normal, we should be looking at it should be passed directly. So we have 1, 2, 3, 4. These are all the values that we populated for the normal struct, and they are passed directly. So this confirms our theory. And if we want to see the Swift.native function API in action, the best way to do it is to look at the Swift.native function API, or the test suite, I mean, which is quite extensive. So we call this function getLoadableStruct by like getting its address and passing and like giving it a return value, and it takes no parameters. So we return this loadable struct. So if we were to launch the test suite and then have a breakpoint, if our code works correctly, we should see the prologue, which is right here, which writes the registers from x0 to however many registers this type occupies to our return buffer. So this is the prologue that we'd be looking for. Yeah, so let's launch the test suite and look at this. So dummy, it's build, LLDB, build, and runner. And we need the mangled symbol right here. And come to think of it, we should have an API to demangle symbols, which is very easy to do because the runtime actually includes this. And let's launch the test suite. So now we are in Swift code. It's dummy.getLoadableStruct, and let's finish. And there is our prologue right here. So it loads the address of the return buffer, and yeah, there is our values which we return from getLoadableStruct, which is the value of the struct itself. Yeah, so this is the Swift.native function. And if you're interested in the protocol composition, feel as well to check it out in this test, in the test suite. So yeah, this is the calling convention and its APIs. So instrumentation, now that we have the metadata and we're able to call Swift native functions, it makes sense to have like JavaScript wrappers for Swift objects and values, and be able to manipulate those objects and values by calling Swift functions on them. So this is basically what we do, and the API that we have for this is the new Swift.object, new Swift.struct, and the Swift.enums to get an enum case. And even if there is a payload, the case name would be a function that you're able to pass your payload to. The reason, like the Swift.enums, you don't usually have to construct them manually, but if in case you want, there is the API new Swift.enum. But for most use cases, Swift.enums would be sufficient. And the instrumentation itself takes place in the first three APIs are for the constructing JavaScript wrappers. The Swift.interceptor API, this one is for intercepting a Swift function and parsing its method name by its signature, or parsing its signature and figuring out the types of the arguments. And because we have this kind of metadata about the types and the values, we'd be able to construct the struct or objects from this metadata or type names and return values and so on. So let's see what the instrumentation API looks like in practice. So I've prepared this instrument.js. We have in our test suite, we have the simple class, if you remember, and we attach to the constructor, and the constructor, this is like the unsugared name of the constructor in Swift, and this is like the JavaScript friendly signature, and this is the address of the function itself. We retrieve it, then if you look at the code in the dummy file, you have simple class. It takes an integer. An integer, by the way, in Swift is a struct. Almost everything is a struct. There are some native values, but those are not exposed publicly. Or yeah, I'm not completely sure, but the point is integers are structs. So what happens under the hood is that it retrieves the metadata of the arguments via their name, and they parse them by passing them the required number of registers that this value would occupy, and just passes those to us. So we have the first dot handle. We read the value, like the raw value of the integer. We read the first and the second. And another thing that we hook as well is the ninth method, which we should be able to access by name, but this is on the to-do list, is the print value for. So this method takes an on-off switch enum, which has two cases, on and off. So if we pass it on, the value, like the tag or the raw case index, should be 1, because 0, then 1. And then, yeah, we initiate it, then pass it this enum, then we print the tag of the enum. So let's do dummy instrument.js, no pause. So yeah, as expected, first, this is like the decimal representation of this. Second is this. Then switches on is printed, and our tag is the one that we expect. Currently, there is no support for replacing values like the original Frida API allows you, but of course this is on the to-do as well, and it shouldn't be very hard to implement. So the future of the bridge. There's a huge to-do list, but as always, but the aim is to bring this bridge to its first production-ready stable API, and the to-do list is prioritized. So first of all, we have some performance improvements that we want to make. Should be easy to do and low-hanging fruit, and should be fun as well. We have as well to parse the rest of the metadata. We have to support optionals, and the list is ever growing. So yeah, that is mostly it. Feel free to hit me up with any questions if you want to contribute to the bridge. And yeah, see you next time.
This is Radius, fast symbolic execution with Radari 2. My name is Austin Emmett. I also go by Alkali, and we will get into it. All right, I am a mobile security researcher at NowSecure, where we automate security tests for mobile applications. I went to school for physics and mathematics at Rutgers University, and I wanted to do loop quantum gravity, but it actually turned out that it was very difficult, so I do this now. And I'm a fan of fancy schmancy techniques that are really useful, things like symbolic execution, but I'm trying to make them more useful and get them into the realm of practicality. So I'm going to start with a demo. Okay. So this is a crack me called r2con2021. It's just a pretty simple program that loops through some possible solution characters, and if you have the right combination, it results in the flag value. So we can use symbolic execution to solve this. As you see, executes very quickly. Takes about 0.5 seconds with all the output, but takes about 0.25 with no output. And we get the flag rotors. We can also see the symbolic PC addresses here and all the instructions that get executed along the way. All right, so you have to figure out first what is symbolic execution, though. So symbolic execution explained in quotes, because it's going to be very short. For a more thorough investigation, you can see my presentation from last year, r2con 2020, which has a more thorough discussion of what exactly symbolic execution is. But in general, it refers to the emulation of a program with the option to have symbolic values. So instead of having something like register Rx set to 8, which is the concrete value 8, it's set to X. And operations on this value are kept track of in a structure called an AST, or an abstract syntax tree. So you can think of X as a kind of an algebraic variable, like you saw in algebra class. It's something that represents an unknown quantity, but that can be solved for later. So as an example, an instruction like add RAX4 would result in the expression x plus 4, which would be represented by a tree like the one here, where we have the expression broken down into an operator and its two arguments, x and 4. So over to the right here, we have a blocks of a function. And so if you imagine having symbolic values stored in one of those memory locations like var50h, when you compare that value, like down there where it compares the quad word at var48h with 0, and then you have the jump not equals instruction, you build up an expression for PC, the instruction pointer, that is then solved for to continue execution after that fact. In the next slide, we'll see an example of this, but PC will be a symbolic value that encodes the comparison here. So if it is equal to 0, it will take that false path and go to the next instruction. And if it is not equal to 0, that constraint placed on it by this jump is true, and so it'll go to 4007C3. And so by evaluating that expression for the instruction pointer's value, we can split the state, and in each resulting state constrain PC to be one of those possible values. Okay, so here we see a little bit of debugging output from Radius, and this shows that we are executing these instructions, and then we have a comparison, just a byte comparison between DL and AL, and a conditional jump, a jump not equals, similar to before. And this results in a PC register value that is represented by this expression here. This is just how Boolector, the SMT solver, represents the AST in typographical form. And this is what is evaluated and then constrained in each of the resulting states to select which path is continued. So we can see at the end of this expression we have those two addresses, 4007DF and 4007EA, as possible values, and then afterwards we see that in fact those are the next two instructions that are executed, 7EA and 7DF, and those are executed in parallel in each of the two resulting states. Last year at r2con 2020, I gave a presentation about SILSolve, which was a symbolic execution framework written in Python that executed R2's intermediate representation, SIL, which is a valuable string intermediate language. And that turns instructions like add EAX4 into a string like 4, EAX plus, EAX equals. We'll see in the next slide exactly how that's interpreted, but that's the actual thing that is executed by SILSolve and now Radius. SILSolve uses Z3, which is an SMT solver, to create those symbolic values and also to solve the generated expressions. And for more details about this, you can see my presentation from last year. So to recap a little bit of a SIL, this is going to be very brief, but a SIL is a string of values, registers, and operations that can represent any instruction from any architecture. Values and registers get pushed onto a stack and are popped off by operators, which push their results back onto that stack. So something here, like we have move RDI, RAX. The expression is just RAX, RDI, equals. So RAX gets pushed to the stack, RDI gets pushed to the stack. The equal sign pops RDI off and then sets it equal to RAX. So it just sets the value of RDI to be the value in RAX. A more complicated expression, like the one for jump not equals, that's takes the value in the 0 flag, push it to the stack. The exclamation point performs a logical not, a Boolean not. So if it's the 0 flag is not set, then we run this conditional expression inside of those brackets. And so that address is pushed to the stack, RIP is pushed to the stack, and then RIP is set to that address. And that performs the action jump not equals. Again, for a more detailed discussion of exactly how a SIL works and also how it is executed by a SILSolve and in a very similar way, the current tool Radius, you can see my talk from last year. Okay, so why rewrite a SILSolve into this new tool Radius? The biggest reason is that Radius is written in Rust, which is much, much faster than Python. Python is very slow. And SILSolve also just wasn't designed in a way that made multi-threaded execution easy or worthwhile to do the overhead of doing it in the way that SILSolve was set up for, just was too much to make it worth it. On the other hand, Radius, which is written in Rust, is very fast. Rust makes it easy to write safe multi-threaded programs, and it's also very trendy, and I want to be cool and get those Twitter likes and retweets. So all around, it's a very compelling reason to rewrite it. So an exploration of Radius versus Silsolve. We have Radius executes concrete instructions like 2,000 times faster than Silsolve. It executes concrete instructions around 2 million, 3 million per second on my machine, which is a M1 Mac. Instructions using symbolic values are executed roughly 20 times faster. So that's mostly just through the overhead of operations in the instruction and surrounding fetching the instruction and tokenizing it in the case of Radius. Radius uses the Boolector SMT solver instead of Z3, which is what Silsolve uses. And I think for solving, they are comparable. The way I had Z3 set up might have been slightly faster, but Boolector makes up for it in being slightly faster to actually perform operations on bit vectors. Another thing that's different is the processor is no longer nominally a part of the states. So the state is the register and memory values, and in many other symbolic execution tools, the processing is done within the state. But having processors act on the states allows them to be executed in parallel by having multiple processors, each assigned their own thread, and just kind of churn through their own queue of states. And it makes it just an efficient and safe way to do parallel processing. States also contain a user-defined list of arbitrary values called context, and so that helps share information between different hooks. When you set hooks during the execution, you can share arbitrary values between them by registering them in the context. So Radius does not just use bit vectors. It has two types, the concrete value and the symbolic value. And the concrete values are simply U64, unsigned 64-bit integers. And that's actually all a SIL needs. And this is part of what makes Radius so fast, is that it does not have the overhead of using constant valued bit vectors, which other symbolic execution tools do. And that's the good thing about a SIL, is that it only ever uses unsigned 64-bit values, and if an instruction needs assigned 32-bit value, it has to make that itself. It's encoded within the instructions, the types, rather than having the types be separate. And another thing that Radius does that makes it a bit faster is doesn't keep copies of unsatisfiable or inactive states. Instead relies on hooking and context to deal with unknown conditions that require examining many states. Okay, so here's a chart that just shows the execution time of various programs in various different symbolic execution tools. Manticore was broken for me, so I just have broken there, which is kind of mean. I should have just taken it off. But first we have Short Looper, which is a program that runs about 2,000 instructions. Radius performs in about 5 milliseconds. Anger without Unicorn support takes about 2 seconds, and with Unicorn, which JIT compiles the concrete instructions and runs them, takes 0.183. So that's mostly the overhead of doing that compilation, switching to Unicorn, switching context to Unicorn. So Radius is much faster. Long looper is another program that only executes concretely. It's about 1 million instructions, and it runs in a quarter of a second for radius, and about the same for Anger plus Unicorn. So in the long run, Unicorn will be faster, but since it requires that overhead of initialization, context switching, in most practical cases, it will be slower, and much slower than Radius will be. And additionally, Radius executes instructions individually. So a concrete instruction by itself, it can execute very quickly, whereas Anger needs there to be a basic block that's entirely concrete in order to switch contexts. And so then after that, we see some just some crackneys that are solved with symbolic execution, r100 and r200. Both are solved extremely quickly by Radius. Even r200, which requires lots of state merging, is solved very quickly. Merges with 48 different states and executes hundreds of instructions and solves the constraints on them all in a third of a second. So we can see here that Radius is generally much faster than other symbolic execution tools, and all these are very short programs. You would see even bigger differences in longer running executions. So how does Radius achieve this speed? Well, Anger is written in Python, which again, like Asilsolve, suffers from the slowness of the interpreted language. But in other ways, the speed of symbolic execution is very complicated. So there's speed of initialization, of executing the instructions, and of concretizing values, solving the generated expressions. So R2 provides quick initialization, loading of the binary, loading of the libraries, tokenizing the asil gives very quick execution. And Boolector does a good job of solving values quickly, but one of the more important things is Radius's use of lazy solving, which basically avoids checking for satisfiability, evaluating expressions when it's not strictly necessary. Otherwise, without those tricks, concretizing symbolic values will dominate the runtime of most interesting symbolic executions. And so one of the difficulties of optimizing these things is that SMT solvers are very weird, extremely weird. They do not necessarily behave the way that you would expect. Oftentimes, something that you would think would be much quicker ends up being dramatically slower. So an example of this that I found recently was when I was trying to construct a symbolic A2I, and instead of having a 32-bit wide bit vector by just slicing the bottom 32 bits off and working with that in order for it to be the right size, it was dramatically faster to take a 64-bit value and just constrain it to be less than the max, in max, the max 32-bit value. And it's like, the difference between something taking a tenth of a second and taking 15 seconds. So it's pretty different, even though it's equivalent in this scenario. And so that's the sort of thing it's really hard to predict what's going to give you good performance and what isn't. So another great thing about Radius is that it does very fast merging. This refers to merging of states. So with Radius, you can set a merge point and you pass it an address, like on the example here on the left. And when states reach that address, they are set aside for merging. And then the next state that reaches that address is combined with the state that was set aside by taking each of the register and memory values, and if they're different, constructing a new value such that if the constraints of the first state are satisfied, then that value is the first state's value, and if not, it's the second state's value. And then that is the state that is set aside, and the next state that reaches this address is merged in as well, in the same way. And eventually, if there are no other states being executed, that state is popped out of merges and continues on. And it now encodes all the different constraints from all those different states, but they have all just been combined into one. And so this procedure can be used to avoid state explosion, or to fix state explosion, by taking a point after a loop where many states have been generated, and then collapsing them all down into one, so that execution can proceed much quicker. You don't have to step 100 states, you can just step this one that contains values constrained in a way that it represents all of them. So here in R200, we have a merge point at 4007FD, and it does exactly what I was saying. After a loop that causes many states, it merges them all together, and then this is actually in an inner loop. So instead of multiplying the number of states in the inner loop with the number of states you get from the outer loop, which would be gigantic and not feasible to actually execute, you merge all the states from the inner loop together, and then you just execute through the outer loop, and it's a very quickly solved problem, as we saw in the demo. This is the demo program. It's solved in about 0.25 seconds. So here's a little bit of the Radius API. To instantiate a new Radius instance, use new, and it's passed a path to the binary that you want to analyze. And then there are multiple methods to create an initial state. So there's call state, which is sets up a stack and heap, and will set the address to generally the start of a function. It doesn't actually have to be the start of a function. There's init state, which does just a state that has nothing. There's blank state, which takes the non-initialized parts and sets them to be unconstrained symbolic values. And there's entry state, which takes an argv and an env list of strings and initializes the binary as if it's starting from the entry point. So with that state, you can pass it to run after setting breakpoints and avoid points. So those are points that you want to reach and points that you want to avoid by setting those states inactive when the execution reaches those addresses. And then also you can set merge points. And then the run method takes that initial state that you create and also a number of threads that you want to use and performs the symbolic execution. Okay. Another object that you'll be dealing with a lot is the state. It has a number of convenience methods to help you create concrete values and symbolic values. So you can see here on the right, you can create symbolic values by passing a string and a size field, which is the number of bits wide it is. You can create a new concrete value by passing a U64 value and also the number of bits it is. There are the memory methods that let you read, write, you read strings and write strings to memory. You can also use it to search memory in a fully symbolic way and compare memory in a fully symbolic way. So you can pass an address value, value to search for, and it will return a value that represents symbolically where that searched for value could be found. This forms the basis of the sims for things like memcompare and memcopy. All those things can be done fully symbolically, and that also prevents state explosion from having to emulate those functions themselves. Simulate is how those are registered. So there are defaults for those sorts of memories: strcopy, memcopy, strlen, tons of different ones. You can see the full list in the sims directory of the repo. You can also set hooks with the hook function. It takes an address and a callback function. And we'll see an example of that later. And then the state context, which is that user-defined list of values that you can use to keep track of different things across hook callbacks, across sim procedures. So Radius does have Frida support through R2 Frida, so you can have a real state. You can initialize with a real state using Frida or actually a debugger. So the way you do that is you use the normal R2 Frida URI scheme, and you then, instead of using call state or blank state, you call the method Frida state, which sets a hook at the provided address and blocks until the hook is hit, and then suspends the app. Then you can run your symbolic execution, and then at the end you can either close or continue to resume the app. So the reason that it's suspended is that you don't want the app memory, which is going to be read during the execution, to change, possibly to invalid values while you're symbolically executing. And also it gives you the chance to solve for a certain state that you want, and then write back the values to the initial state that will get you there. So we're going to see a demo of that exact thing here. Okay, so here we can see both the terminal and the iPhone now. This is running a Crack Me made by my colleague Francesco for Black Hat 2019. It's kind of like my standard iOS test Crack Me. So we can run the Frida example, which hooks the validate method that validates the serial number. So now that it's hooked, we can enter in anything, and it'll start running. And we can see here that it is executing. It then finds the correct flag, writes it back into the right spot in memory given by the X0 register, and then solves the challenge. Okay, so plans for the future. I want to improve the architecture coverage and fidelity. That's in R2. So have ASIL expressions for more instructions, including more floating point instructions and vector instructions, which right now are not covered very well. Have better sims, which are those functions that are there to simulate standard library functions that might cause state explosion or may not be executed very well symbolically, and just replace it with a function that is a faithful symbolic representation of that function. And I also want to integrate radius into libafl to make a binary only fuzzer. It's guided by symbolic execution. It'd be like a very powerful way to explore the whole state of every possible state of a program. So it's very useful for fuzzing, and just the speed of radius makes it a lot more practical as a way to do guided fuzzing than other symbolic execution tools have been in the past, especially ones that are binary only. And so I also want to have better DEX support so we can fully symbolically execute Android apps and seamlessly transition from the Java runtime to native code. So native code right now is handled pretty well. ARM64 code is handled pretty well, but the DEX needs work. So I've been working on that. And yeah, that's it. I hope other people will enjoy the tool and contribute to it. If you find issues with it, please let me know, because I want to keep up with everything, and I want it to be something that is useful. So thank you to Pancake and the whole R2 community, and hope you enjoyed the presentation.
So welcome to my presentation. I'm Pancake, and I will be speaking about how to debug Game Boy ROMs using r2frida. I'm gonna be taking an approach that is kind of interesting, and I think that many people will be curious about how that works, and also it's a technique that can be also applied to different targets like other emulators, virtual machines, etc. So first of all, who am I? Pancake. I'm the author of r2frida, and many other open source software around. I'm working as a mobile security analyst at NowSecure, and well, I'm gonna be explaining, like I said before, about how to toy with Frida R2 and the Game Boy, and also we will have a look at the source code of SDL GNU Boy, the emulator that I took as an example for playing with that. And yeah, and also we'll be showing how to use r2frida for managing all this. So it's demo time. Let's go into the r2frida source code directory. In here, you can see that there is some different directories, and the interesting one for us is the plugins. In plugins, we have different examples of different scripts that can be loaded into the r2frida agent session that you are running. These plugins are specific to r2frida. This is not a Frida script, but it can be easily tweaked to make it work on Frida directly also. So I will take a look at the GNU Boy JavaScript. You can install the emulator using r2pm. And then you can run the thing using r2pm-r GNU Boy and the name of the ROM. How to touch? Okay, we will need to use Frida to specify the action and then the process name. If you look into the output of Frida question mark, you will see that there is different ways for loading the and spawning the process. And you can, for example, pick like a full path in local. You can specify a binary that is supposed to be in path. You can also specify that you want to spawn or you want to attach, and then you can also specify if it's a USB remote device or a TCP, then specify the device name there, and then the application name or whatever. Okay, so after doing this, we'll have to load the plugin. As we know, all the commands in r2frida start with the 2 dots. And there is a dot command, which stands for loading or importing or interpreting or scripting or, yeah, you know, taking the script that you have in your home or in your host and put it directly into the agent side. As long as r2frida is providing a bunch of different APIs to expose a plugin interface and new comments to the host site, using that, you will need to use the r2frida global object for changing this. So this is the source code of the plugin. The plugin allows you to clear the screen of the emulator, mute the audio. You can also continue the execution, perform one step, stop, check the register values, and you can also swap between IO and non-IO memory. I will start explaining how that works because that's probably the most interesting thing that you will be able to apply to different use cases. The first one is IO and no IO. Okay, so if you use the no IO command, it will be setting the hooked read and hooked write callbacks to null. But if you use the other one, the IO, it will be changing these hooked methods. So basically the r2frida backend, it's checking if these methods are null or not, and then it will be calling them to replace the default behavior. So by default, you will be reading the process memory of the emulator itself. But if you enable that, you will be reading the memory of the Game Boy itself. So the RAM memory of the emulator that you are introspecting with r2frida. Okay, let's take a look at the source code for these functions. So the hooked read function stays in there. And you can see that it's basically creating an empty array. It's iterating for the amount of data that you want to read. So you take the offset and the count, and then you return an array with all the data. And the hooked write works more or less the same. So you get the offset, the data, and you basically return an empty array because there is no errors handled there. Okay, so what's going on in the nuvoid read? The nuvoid read is a symbol which gets resolved by the native function module find export by name that is named memread and memwrite. These two functions are specified in the source code of the emulator, and these symbols are public. So even if you don't build or you strip the thing, you can. I mean, if you strip the binary, you won't be able to get the symbol, but you can quickly or easily find the pointer to it. But otherwise, I will recommend you, because we're just developing that or playing with this, and I will recommend you to just build the SDL GNUBoy by yourself and just pick the symbols from a build with the back symbols. So this function takes an integer and returns an integer. And the memwrite basically takes two arguments, which is the address of memory and the value that you want to write there. So you are basically reading byte by byte with these two functions. That's a little slow, but you will see that it's not that slow. I mean, performing is pretty well. Okay, so after this, we will see that there is other actions that we can do there. For example, the show CPU, it's parsing the structure that is named CPU. That is basically a structure that contains the following registers. It's not just registers, but also some configuration options for the Game Boy emulator. So you can take the program counter, a stack pointer, and other registers, and speed, HAL, deep, etc. The cool thing is that this way you can basically use R2Frida to instrument an emulator or virtual machine and read and swap from the process memory to the virtual machine memory and introspect all the CPU registers of this virtual machine and also instrument the stepping. So you can basically implement a full debugger on top of an emulator using the same logic. Okay, so what's next? The next interesting thing, I will explain all the source code at the beginning and then we will jump into the demo. So when you do the CPU stop function is checking if the CPU emulate is hooked, and if it does, it's just doing nothing. But if it's not, then it will be intercept the method. The method that is intercepting is the one named CPU emulate. You can find this by sim. This one. We have the CPU emulate symbol that takes an integer. The integer that takes as argument specifies the amount of cycles that you want the emulator to execute. So if we basically return at this point, we're stopping the emulator. The CPU won't be executing any other instruction. But if we execute that passing 1, you will be executing 1 cycle. That doesn't mean that you will be getting like a full instruction, but you can step into the cycles level. The reason for that is because console emulators used to depend on synchronization for video, audio, and CPU, and all that stuff requires to be working with clocks and not instruction cycles. Okay, so what we're doing here is basically hooked and intercept the CPU emulate function, because this way we can replace the implementation and do a stepping. So how to do stepping? In order to do stepping, we first need to check if the CPU emulate function is intercepted. If not, then we'll be stopping the execution. But if the execution is stopped already, we basically say that the function is not hooked. So we can call CPU emulate with 1, and then we can replace that with 0. The reason for that is because we have replaced the implementation of the CPU emulate callback, which is a function that we have defined by replacing it with an interceptor. So we will not be able to call the original implementation of the function unless we call that from inside the same replaced function. The reason for that is because if you try to replace and remove the interceptor on one specific function and you remove that at runtime, you will probably get crashes. because Frida is able to add some blocks or mutexes when you are hooking a function, but you're going to do that when you are removing the interceptor for one method. So it's better just to only replace the original method and then just go into just changing the implementation of the logic. Okay, so yeah, let's close the script. We'll copy that into the /tmp, and we can go into the GNUI source code. We can check the code. We'll see that there is the emu. We see the CPU emulate function, which is implemented inside the CPU. And you'll see that it's basically, I put some printfs there just for debugging, but you see that the explanation that I did before is the one that is matching here. So we don't really need to understand or modify anything below, because this is basically handling all the instructions for the Game Boy CPU. But we only need to change the behavior that happens at the beginning. So we replace this function with a function that does some checks, and if the checks are not matching, then it calls the original function. Otherwise, we'll be returning without executing any instruction. Okay, so we know how to run the thing, so let's follow instructions that we read in the document. So first of all, we need to run the emulator. SDL source. Oh, sorry. SDL GNUI, and then we have some ROMs. So we can get you see that the emulator is running. We can interact with it, and we can see the log messages that are printed in the left, that are basically the instructions that are getting executed. So how many cycles is getting executed, to get in sync with the video and the audio. Okay, so we have the emulator running there, and we will attach the r2Frida. So we have the emulator there, and we will pick the process using r2Frida. You see that we are now intercepting the process, and we didn't have to break the execution. So we can use the question mark I to get some details on the process in order to check that we are actually checking the real process. And the next thing that we will need to do is to load the plugin for Nuvoy. The plugin was named Nuvoy. And we'll prefix that with a colon. With this, we should be getting the GB command. This command is executed in the agent side, so we can basically stop the emulator. It will stop listening to music, and you keep listening the noise. Actually, we can continue that, and the emulator keeps running. So the next thing that we want to do is to check the IO thing. So right now in the address 0 there is nothing. We can check that in other places we can see some memory. But if we replace the real process memory with the emulator memory using this function, we can see that now we see nothing, but if we seek in the address 0, we see the memory of the Game Boy. So this is the contents of the RAM of the Game Boy emulator. So we can replace, modify anything in there, and that will be changing in live. Okay, so let's go back and let's read the real process memory. So that's nothing there. We can seek into the process memory. And okay, so next thing to do is to do some stepping and check the register values. So using the GB CPU, GB, we'll get this script for R2 that we can execute using the dot. So if we do that, we will see that the CPU, so this command is basically showing the address of the CPU structure, and the value for this is that. So as you see, only the sound is changing because we are actually stopping the execution always in the same program counter, because the game is not running out of this loop. But if we run the thing pretty quickly, we'll probably change the execution. So the next thing we can do is basically check the code in this address. So we will enable back the IO, and we can seek to this address, and we can change the CPU. So this is the code that the Game Boy emulator is running right now. So yeah, that's more or less a quick demo. If you have any question or whatever, please drop me a chat in Telegram or Discord, and I will be happy to help you. And as I said, let's close the music. Okay, no more music. Or there's skip running, but at least there is no music in the background. So yeah, hopefully you enjoyed the presentation and you learned some new stuff and some applications. So as I said, you can also use the same script to with some few modifications to make that work on QEMU or VirtualBox or VMware or any other virtual machine that you can imagine, and same goes for any video console. And together with all the amount of CPU supported by R2, you can get a lot of things that you can target with this to free the script. Thanks for watching. So all the conference presentations are done right now. We are gonna do the last run of R2 Wars. This will be the real competition, so stay tuned and try to focus on all the bots. We have more bots than the last day, and I would like to remember that the first 2 days it was just only training for the bots, and today is the real competition. So yeah, let's begin. seems like we have the winner. Congratulations, Amphibia, you got the first position. There is also Old Flacucho who got the same position. This means that we have 2 winners for this round. And yeah, I would like to say thanks for everyone who have submitted their bots for playing. It was really nice to see all the bots playing around and seeing their strategies for winning. So congratulations to Kamehameha, also to Shiro, Zeta, Ricardo Apiel, Newbot, and Amaterasu. Congratulations everyone for playing, and well, let's go into the waiting scene again, and we will then go the closing keynote. But don't close the stream yet. There is a chiptune concert after that. So we are in the closing keynote. Thanks everyone for attending the conference. Hope you all enjoyed the event. And remember, this is not the end. This is just the beginning of the end. So hope you all enjoyed the conference. I hope you, it was a pleasure to gather all of you, and hope you have a safe trip at home. Well, I guess that you are already at home. But wait, don't close the tab. There is still some stuff to explain and a big chiptune party after the event. So first of all, we need to announce the winners for r2wars and the CTF competition. So let's go for the capture the flags. So this year we got 130 users registered. The Witch challenge was the one that was most solved. It was solved by many people, and only 2 challenges was not solved: the mixtape and the molten core. You can see there in the graph, which was how many people have been solving them. And this is the final ranking. We have a clear winner, which is who got 1,362 points. And yeah, we send a mail to wait for and expect your write-up explaining how you managed to solve all of the games for the CTF. But yeah, I would like to thank everyone who have been playing the CTF, not just for the winner, but also all the other players. So it's like 150 people. I'm just gonna be enumerating the first one, which is Ayanoi Koji, Ignite, and Goyo, and Buff. So thanks for all the participants, and big congratulations to the winner. For r2wars, we just did the final round a few minutes ago, and we got the 2 winners. There was 2 winners because there is a couple of people that got this the same punctuation, so they won the same amount of rounds and they lose the same amount of rounds, so they got first position shared between them. So congratulations, Goyo and Ricardo Lopez, for your bots. Goyo wrote a bot that was named Amphibia, which was pretty smartly written and seems like it's been winning also in the previous days. And we got the Theta, which was also competing really well and got the first position. So congratulations to you all. Stay tuned because we will contact you to send you the prizes, and hope you had fun also participating in these tournaments. But remember, this is not the end, because now we have the chiptune party. Huge thanks for all the artists that have been playing this year. So we'll be playing, first of all will be Game Jenny Sokolov playing. Then we have I lost the order right now, but yeah, we'll be playing them. They will be playing after that. So yeah, a big thanks to Edge, also Watch Out for Snakes, Havoc, Boltkit, 4D Boy, and Genjani Sokolov. Thanks everyone for attending this year. It was amazing experience, as it is usually. We really missed the physical event, but yeah, I mean, making it online is not that bad. At the end, we have everything recorded. I'm really sorry for all the technical issues that we have suffering this year, but we managed to get over them. And also a reminder, I have all the original recordings for all the streams that have been messing in live. So we'll be slowly publishing all the original videos with proper details and explanation. So it will be easier for processing than just watching 8 hours in a row. So thanks everyone for coming, and now it's time to have some fun.
Warning, this disc is for use with a Sega CD system only. This disc contains CD-ROM data and is not for audio use. Please press stop on your disc player now.
Neptune. r2con.
Free, no string.
10:25.
mort ou un blessé par jour par la police depuis le 1er janvier.
On the low, only let myself no more. Take it to the grave, I'll ghost. I know I can be so cold. In the dark, I like to keep my heart. No more bite, no bark. Like to catch you way off guard. I'll stay so deep inside your brain and take you somewhere far away. I'm a straight up villain, straight up villain, yeah, villain, yeah, villain, straight up villain, straight up villain, yeah, villain, yeah. But I'm dead, hear my voice up in your head, watch it flee through the bed, is it really just a past? I'm playing with your mind, and I'm treating like a god, and I'm waiting to decide, and am I really that bad? I love to make you mad, and get happy when you stand, only feel better bad, in control, that's how I like it, and I'm never letting go, never had a soul, so you ain't taking nothing from me when you go, I'll spend the morning days, you don't understand. Dancing with my life, not expecting that. Dancing with the past, dancing for the past. How you did, all this little thing. Bang, bang, you can do anything. In the dark, alone. I only know myself no more. Take it to the grave, I'll ghost. I know I can be so cold. But I'm dead, get my voice up in your head.